Chapter 2, Sets and Venn Diagrams. So we're going to start first with talking about sets. So a set is just a collection of numbers or objects. You just collect certain things up, list them, that's a set. The elements or objects, the numbers or objects in the sets, we call them elements or members of the set. So we got a couple examples here. If D is a set of digits we use to write numbers, then D is, so this is all the basic digits you see like on a phone or something. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? And each one of these things is an element of the set. So 0 is an element of the set, 2 is an element of the set, 3 is yada yada. As the nice lady tells us, the curly brackets are read as a set of. So anytime you see the curly bracket, it's like a listing. These are a set of elements to that set. If C is a set of countries with coastlines on the Caspian Sea, then C is Azerbaijan, Iran, Kazakhstan, Russia, and Turkmenistan. Right, so again, it could be objects, it could be numbers, it could be lots of different things. As long as you list them out, you'll be like, oh, this is a set of these things. Some basic set notation. If you see this like skinny E thing, like it says here, that means it's an element of. So a lot of times you write like, let's see, over here, I'll write Iran. Oops. That's me way too thick. Here we go. Iran is an element of C, right? Iran's is in the set here. So that's what that means. When you put a cross through it, it means, well, it's not an element of that thing. So 2 is not an element of C, right? There's no numbers in that element, that set. The low number from the set means the number of elements in that. So in this case, number of elements in C, if I was counting them, that lets me know how many elements are in C, and that's be 1, 2, 3, 4, 5. So that's how you read that. That's how you do that set notation. Finite infinite sets. A set A is a finite set that has a particular defined value, right? If I put, hey, there's a number here, and I actually get a number, right? Like here, like we did here with 5. It's a finite set. There's a certain number for it. Prime numbers less than 20. You can actually count them. It's 8. So it's a set. If it doesn't have a particular value, we call it an infinite set. Two sets are equal if they contain the exact same elements. So if you want two sets to be equal, they have the exact same things inside of it. So to give you an example here, 4, 1, 8, 8, 4, 1. Those two things are equal. And we would typically write them in numerical order, or alphabetical order if it's objects. So typically we write the set as actually 1, 4, 8. Subsets. A set A is a subset of B if every element of A is also element of B. So then we can write A is a subset of B. So all that means is if you take a set, let's set 1, 2, 3, 4, my subsets are everything that's smaller than that, that's also in this. So if this is my B, my A could just be the set of 1 and 2. That's a subset of 1, 2, 3, 4, right? Because 1 and 2 is in this set here. So it's a subset of it. My subset, I can have a subset, a C that's everything. 1, 2, 3, and 4. Alright, it still fits the quota. Everything in here is also in here. So it makes C a subset of B. Once I put something that's not in there, I was like, hey, D is 2 and 5. Well, 5's not in B, so it's not a subset of B. So this is a separate thing. Right, so sets have to be smaller than or equal to the bigger set. And then a proper subset is if every element is also an element of B, but not equal to. So like over here, right, A is a proper subset of B. No equal sign. A is smaller than B. But C is not a proper subset of B. It's actually equal, so you put C as like this. So less than or equal to subset version of it. Empty set, it's a set of no elements, so it's an empty set. So if you said like prime numbers, even prime numbers greater than 5, there's no elements in that. The only prime number that's even is 2, so can't have any even prime numbers greater than 5. So my set there would be an empty set. So let's see. Example 1. Let P be the set of letters in the word amateur. Let Q be the set of letters in the word team. List the elements of P and Q. So, well, P would be the element of A, M, T, E, U, and R. You don't rewrite the same letter twice because it's already collected. So there happen to be 2a's, but you only write it once in the set. And then Q would be team, so T-E-A-M. Again, alphabetical order would be better, but I'm just going quick here. List N of P, so how many elements are in P? There's 1, 2, 3, 4, 5. I'm asking for Q, there's only 4 elements in Q. 6, I can't count. 6 elements in P. Okay. Decide whether each segment is true or false. Is U in Q? Well, here's my Q. No, U's not. You don't use U to spell team, so false. R is not an element of Q. So here's my Q, T-A-M. R is not an element. That is true. P is a subset of Q. So remember, that means that everything in here has to be in here also. That is not true. Yeah, because U and R. So it's not a subset. So it's false. Other way around does work, though. Q is a subset of P, right? T is in P, E is in P, A is in P, and M is in P. So Q is a proper subset of P. That is true. So that's set and subset notation. 8. Consider two sets A and B such that A is a subset of B, but it also could be equal to it. Find the possible values of X if A equals 2, 4, 6 in X, and B equals 2, 3, 5, 6 in X plus 1. So now remember, it's a subset. So I can't make X, if I made X like, let's say 7, right? Well, if I made X 7, then, well, B doesn't have 7. So it couldn't be that value because it has to be a proper subset. So that wouldn't work. So I'm gonna start low. But what if X is 1? If X is 1, well, actually it can't be because then there's no 1 in here. So let's start this way. Let's start with the lowest value in B. Let's start with 2. If X is 2, that means that I get 2, which puts here. So there's 2 2s, that's fine. And then 2 plus 1 is 3, that's in there also. So that would actually work. So X can be 2. So it'd be 2 and it'd be 3. That still fits the quota that this guy is a subset of this guy. So that one works. If I go X is equal to 3, well, then I get a 3 here. There is a 3 here, that does work. And then 3 plus 1 is 4. Now again, there's no, there's a 4 up here, but it doesn't matter. All that matters is that as long as all these happen to be in this guy. That's all that matters. So 3 actually works too. If X is 5, well then, again, if X is 5, I have a 5 right here. That works. And then 5 plus 1 is 6. I get 2 6s, that's okay. And then X is 6. So the only values that could be, X can only be the values here. So 2, 3, 4, 5, and 6. So there we go. Check marks, check marks. 5. Let S be 1 and 2 and T be 1, 2, 3. List all subsets of S and T. Ooh. So my subsets of S. It's a little tricky. So you first you separate them. So 1 counts by itself. 2 by itself would count. And then you go do the whole set 1 and 2. Now this is a little ahead of the game, but what we also consider a subset is the empty set. I'm not sure if they do that in this class. Well, I don't think. Yeah, it has to be an empty set also. It's like this set 0. 0 is always a subset of everything. So empty set's always a subset of all these sets. So there's my S. T. Well, it'll be the same thing. It'll be 1, 2. The set 1, 3. Sorry. Then I can do all different combinations. I can do 1, 2, 2, 3, 1, 3. My curly brackets are not good today. And I can do the set of everything. 1, 2, and 3. Don't forget the empty set. Right, so you just kind of do every single set. You go, okay, 1 by itself, 2 by itself, 3 by itself, 1, 2, 2, 3, 1 and 3, every combination. Is every subset of S a subset of T? Yeah, every subset of S, right? is also a subset of T. 1 and 1, 2, 2, 1, 2, empty set. What fraction, so this is true. Yes. What fraction of subsets of T are also subsets of S? Subsets of T are also subsets of S. 1, 2, 3. So how many subsets of T are there? 1, 2, 3, 4, 5, 6, 7, 8. So that's total. How many of them are also subsets of S? 4 of them. So half. So that's subset notation. Remember, all the subset is just take every element of a set and break down singularity or piece it together. Intersection and union. So the intersection of two sets symbolized by this notation, also known as an AND statement. So two ways to look at intersection. It's this or AND. What it generally means is two sets. The intersection of two sets A and B is a set of elements that are both in A and in B. So if it's in A and in B, then it's an intersection. So look here. Example, if A has 1, 3, 4 and B has 2, 3, 4, the intersection within both of those is 3. So you want to think of intersection as both. Right? It's in A and in B. It's in both of those elements. If two sets have nothing in common, nothing in common, I couldn't talk. We call them mutually exclusive. So they have nothing in common. If my two sets were set 1, 3, 5, and the set 2 and 4, these two have nothing in common. So it'll be that we call them mutually exclusive, and we say it's an empty set. They have no elements in common. So again, it's a little funky. People think mutually exclusive means it actually sounds it is what it sounds like. They're mutually, both of them, exclusive. They're not hanging out together. Union. Union, we use this symbol. It's an OR statement. So the union of two sets A and B is a set of elements that are in either A or B. So it could be in A, it could be in B, it doesn't matter. You just put them all together and that's your union. So my union of these two examples here would be the set 1, 2, 3, 4, and 5. Right? As long as it's in one of the sets, you plug it in. It's in the union. The union is just kind of a combination of both of them. So let's do example 2 real quick. So here's my sets. M is 2, 3, 5, 7, 8, 9. N is 3, 4, 6, 9, and 10. I want to find A, the intersection. M, intersection N. So remember, that's what they have in common. That's what they share. So it's the 3, 4, 6, no, 9, 3 and 9, I think. Right, so the only thing they have to share in common is they both have a 3 and they both have a 9. And then B is the intersection, so U. So I always think union. So you put them together, and this is the intersection. And that's the easy one, just put them all together. So I gotta put a 2 down because there's a 2 there, put a 3 down because there's a 3 there. There's also a 4. There's a 5 on M. There's a 6 on N. There's a 7, there's an 8, there's a 9, and there's a 10. Right? So as long as it's in one of them, it's in the union. You just put them all together. C, let's talk about the complement of a set. So before we talk about the complement of a set, we got to understand what the universe of a set is. The universe of a set is all elements that we are considering. So we don't always just think of all numbers in the world or all elements in the world. It's just, we'll say the universe is some set of values. So it's like U equals this thing. So that's only numbers we're considering. But this is my universe. I'm saying, hey, I want my P to be the primes of that universe. Well, the only primes in this universe here are 2, 3, 5, and 7. Right? There's more primes. There's 11, there's 13. But the only ones I'm considering are these right here. So that's what the universe is. It like narrows your window. It's the only thing we're talking about. Okay, so now that we know what universe is, hopefully, we can talk about what the complement of a set is. The complement of a set A is the set of elements that are in the universe but not in A. So we write that as A prime. So let's do an example to make sure I hit the home. So in this case, my universe is this. It's numbers from 1 through 8. And I'm like, hey, A are just the numbers 1, 3, 5, 7, 8. So what's A prime, the complement of A, is everything that's in the universe that's not in A. So with like all the stuff A is missing. So A doesn't have a 2, doesn't have a 4, doesn't have a 6. So that'll be my complement of A, right? So stuff that's in the universe but not in A. So that's A prime. Three things we talk about when we talk about three things we talk about when we talk about a set and its complement. Well, first, if you look for the intersection, what they have in common, nothing. They should have nothing in common, right? It's a complement. They're exact opposite of each other. So they have nothing in common. If you look at the union, like we put them together, well, if you put these two together, you should get the whole universe. That's what it says there. And then if you count them up, right, the number of items in my universe here, 1, 2, 3, 4, 8 items. The number of items here is 5. And the number of items here is 3. So when you add these two up, you should get this guy. So that's a complement. Let's do a quick example. Let U be the month of the year. So that's January all the way to December. Find the complement of months starting with a J. So what is that? There's June and July and January. So M is just the 3 months that start with a J. So January, June, and July. So there's 3 elements, right? So that means I know there's 12 months in the year, so there's going to be 9 other elements. They want me to find the complement of M. So that means M prime, that's what I'm looking for. The complement of M would be everything else. So it would be February, March, April, May, August, September, October, November, and December. So again, they want me to find the complement of it. So M is this, the complement would be everything that's not that, so this. Months contain the letter A, I'm just going to skip past that, it's the same thing. Well, not the same answers, but it's the same concept. Special number sets. So something you should learn in Algebra 1, there's special number sets, but we're going to talk about a little bit more in detail now. So when we talk about the natural numbers or the counting numbers, it's exactly what it sounds. I was about to say it's exactly what it sounds like, but not all the time. So in some parts of the world, the natural numbers are the natural, like also count the counting numbers. You just start counting 1, 2, 3, 4, 5, 6, 7. And other parts of the world, it includes 0. And I guess in IB, it includes 0. So 0, 1, 2, 3, 4, 5, 6. So keep that in mind. So the natural numbers are 0, 1, 2, 3, 4, 5, 6, 7. I think usually in America it starts at 1. I'm not sure which starts at 0. But IB, 0. The key thing here is actually the symbol. So anytime you see the symbol, that's what it means. So if you see this fancy N, they're saying we're talking about the natural number. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So when you see a little fancy N, that's what you're doing. Z is for integers. Remember, integers are the plus and minus values. So it's like the natural numbers plus the negative values. Or natural numbers are just like positive. Start counting 1, 2, 3. Integers are all those plus the negative version of all those. So that's a Z. Z with the plus sign is a positive set of integers. So again, most parts of the world, these are two that are the same. Q is a fancy one. Q is all instead of all. So Q is rational numbers. So a rational number is something you could write it as a fraction. With natural numbers. So like 1 over 3. It's a rational number. Right? If you could write it as a fraction, it's a rational number. Even things that like they show you here, even things that repeat 0.3, it's a fraction. 1 over 3 is the one I just wrote down. Right? You get a fraction like this. You could rewrite it as a fraction like that. You get rad 16. Well, you know the radical of 16 is 4. You could write that as a fraction. 4 over 1. Right? If you could write it as a fraction, it's a rational number. Key thing here, if a decimal terminates, that means if it ends, it's a fraction. So I gave you something like 0.1231. You can write that as a fraction because it ends. That's just 1231 over what? 10,000? Thousands place? So rational numbers are just numbers you can write as a fraction. You can write as a fraction, it's a rational number. Irrational numbers are the exact opposite of that. So then you cannot write as a fraction. So the classic examples are radicals you don't know, like rad 2, rad 3, rad 5, and pi. E is another one. Those are called irrational. I guess right here they just write Q with the complement, like the complement of Q, A lot of times you also see I, but I guess either way. Then R is a set of all real numbers. So any number you can think of right now that's not imaginary is R. So that's a real number. And basically R is if you put the rational and irrational together, you get R. In general, if you think about numbers, like we start here with our R, it's the biggest set of numbers, then you break off, you have the rationals, Q, you have the irrationals, Q prime, and then lower than rationals are the integers, and below that are the natural numbers. That's usually the way it goes. Right, so you have real numbers, and then you have rational, irrational, and then below the rational are the integers, and below that are the natural numbers. And if you notice, like they've mentioned here, stuff like this, 1 over 0, you can't divide 1 by 0. Radical negative, that's 2, that's an imaginary number. IB doesn't really do imaginary numbers. And since you can't put these on a number line, they're not considered real, so they're not real numbers. So this one here, here's a question. If U equals Z, which remember, the universe is Z, so that means I'm talking about all the integers, so -, -5, -4, -3. I don't know why I started so far. -2, -1, 0, 1, 2, 3, ... Right? That's my universe. All the integers. I want to know what the complement of Z plus is. Remember, Z plus is all the positive integers. 0, by the way, is neutral. It's not positive or negative. It's neutral. So the complement of this would be everything that's not this. So the complement of Z plus would be all of these guys. So my complement, my Z plus prime, would be a set of everything from -3, -2, -1, 0, like that. So everything that's not 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's complement of that. A little historical note here. The reason why you use Z for integers is because Z stands for Zahlen. I get that. I'm probably pronouncing it wrong. Which is German for numbers. So that's why we use Z for it, because it's German for numbers. Theory of knowledge question. The general idea here is we're saying that radical 2 is irrational because you can't make it a fraction, because it doesn't terminate, it doesn't end. Well, how can we prove it? How can I prove that radical 2 is irrational? How can I prove that it never ends? And it's a hard way to prove it. So the question here is, if something has not yet been proven, does it make it untrue? Is the state of an idea being true or false depending on the ability to prove it? So, little food for thought. And actually, there's actually a way to prove it, and I'll talk about that in class. Interval notation, the last lesson we're going to go on today. So, interval notation, I actually have an issue with the IB. This is generally called set builder notation. Interval notation is a little different, but IB calls it set builder notation. It's just how you write things. So like right here, they have the numbers from -2 to 4, and then what they're writing here is x such that x is an element of the integers, right? Because these are all integers, -2, 1, 0, 1, 2, 3, 4, 5, they're all integers. Such that, that's what the line means. Line means such that. So x is the integer such that you're going between -3 and 5. And notice there's no equal to sign here, so you're bigger than -3 and you're less than 5, but you're going to be an integer. So that makes it 4, 3, 2, 1, 0, 1, 2. Now, in IB, we generally don't have you write answers this way, but we do have you read them this way. So you'll see in problems all the time where it'll say, oh, x is the element of the integers. That's just letting you know, hey, when you get an answer, it should be an integer. Or they'll say x is the element of the real numbers, which generally means it's an element of it's to be irrational, to be like a decimal or something. Usually when they write something like this. Well, that's what this means. So you're like, oh, x is the element of the real numbers. It could be like anything. It could be a decimal. It could be a fraction. It could be an irrational number, right? It's going to be something between. It's going to be something kind of ugly. And then you're between -2 and 4. So we can. So you see this line, this number line here, right? So you're every number between -2 and 4. Notice how you're everything between -2 and 4. There's no like dots here. It's everything. So that means you're a real number between -2 and 4. Notice how -2 is in a closed circle. So we put a line because that means we can be -2. It's included. and then 4 here is an open circle, so we can't be 4, so we put with a normal less than sign, no equal to value there. So we're saying, hey, x such that x is between -2 and 4. And also notice here they don't put the real numbers, because anytime we see an x by itself, we just assume it's a real number. So when you see an x by itself, like, oh, it's a real number. When you see something there like, ooh, it's an integer, that means it's gonna be all the nice numbers there. So let's do a few examples. Write down the meaning of this interval notation. So x element of z such that, so it's an integer, it's all numbers between -3 and 10, or 10 is included and 3 is not included. So I don't know, it's the integers between 3 and 10, 10 included. Generally, we write that. So list the element of set A. So again, remember it's integers from 3 to 10. Now remember 3 doesn't count because it'd be bigger than 3. So 4, 5, 6, 7, 8, 9, 10. Those are all the elements of my set here. Find the number of an A. So how many things do I have? 1, 2, 3, 4, 5, 6, 7. So the number element in A is 7. Write an interval notation, set builder notation, really. The set of all integers between -100 and 100. Now again, it's integers, so that means I have to say x is an element of z such that we're between 100 and -100. So when you're between, we don't consider it included. So something like that. The next one, the set of all real numbers greater than 1,000. So this one, all numbers bigger than 1,000. So this one's a little easier, right? You just go x. You don't need to put its element of the reals because it is a real number. That's what we assume. And this x is greater than 1,000. So that's how you write in set builder notation. By the way, this one written in actual interval notation would be x is, you're going from 1,000 all the way to infinity. Because if you think about like a number line, here's 1,000. Here, everything greater than that. So that's how you write in interval notation. This is like set builder notation. So again, write interval notation. Again, if I was doing this in normal interval notation, I'll just say it's from 8 to infinity. Now this is a closed circle, so we have to write a bracket there. If you want to do it in set builder notation, you'd be like, it is a full line, so we're going to say x such that x is greater than 8, equal to 8. So there's my set builder, there's my interval notation. This one's one you can't rewrite as interval notation because there's points, so you just list them out, that's the way you do it. But you could write them in set builder notation. You go, hey, there have to be integers, so x is the element of the integers such that x is between -3 and 4. Right, so between -3 and 4. You're less than 4, but you're bigger than -3. By the way, you can also do that if you wanted to. You could say you're between 3 and -2 inclusive. If you want to include the 2 endpoints, you could do it that way. Equivalent. This one, if I was doing set builder, just do the way you see it. So x such that x is less than -5 or x is greater than 1. If you want to do interval notation, you would say you're going from -infinity to -5, 1 to infinity. Right, so if you're doing like the set, you're going to go from if you're doing like interval notation, you go like, I'm going from -infinity to -5, 1 to infinity. Suppose the universe is the universe of integers between -5 and 5 inclusive, and A is the set of integers from 1 to 4 inclusive, and B is a set of integers from -3 to 2 inclusive. List elements of A, B. Okay. So those first two are going to help us a lot with the rest. So I want everything that's in A. So I'm going between 1 and 4 inclusive. So it's just going to be 1, 2, 3, 4. little set brackets. Right, because again, we're going everything from 1 to 4, but the only thing we're counting is integers. So 1, 2, 3, 4. B is everything integers from -3 to 2, but we don't count 2. So we're going to go to 1. So B is -3 counted, -2, -1, 0, and then 1. Remember, I can't be 2 because it's not included. So that's my A, that's my B. I think it helps if we do the universe. So we're starting at -5 and going all the way to 5. So -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. Like that. Right, so that's my universe. A is only from 1 to 4. B is from -3 to 1. What's complement of A? So remember, that's everything that's in the universe but not in A. So it's everything except for 1, 2, 3, 4. So if I was going to write it, it would be -5, -4, -3, -2, -1, 0, and then 5. Complement of B, again, that's everything that's in the universe but not in B. So you take it, like, you basically cancel out this guy right here, and it'll be -5, -4, 2, 3, 4, 5. What's in the intersection of A and B? So what do A and B have in common? It looks like 1's the only thing that's in the intersection. Right? The only thing they have in common is 1. What's in the union? I think the union is the easiest part. You just put them all together. So -3, -2, -1, 0, 1, 2, 3, 4. Now look, this one looks scarier, but we already have what A intersection is. A complement is. A complement is all this. So it wants to know what's the intersection of all this and B. So here's my B. Here's A intersect have in common. It looks like they have in common 0, -1, -2, and -3. Right? That's what this guy and this guy have in common. A and B. A prime and B have in common. The next one says A prime and B prime, I want the union of them. So as long as if it's in one of them, it's in the union. Right? I always think about the union is you're just kind of dumping those two things into the same bucket. So I'm plugging both of these into like this bucket, and I get this -5, -4, -3, -2, 0, 2, 3, 4, 5. Like that. I just put them all together. And the last one, suppose the union is Z pluses. Remember that is just 1, 2, 3, 4, 5, all that stuff. P is multiples of 4 less than 50. Okay, that sucks. So 4, 8, 12, 16, yada yada. Q is multiple to 6 less than 50. 6, 12, 18, 24. List P and Q. Oh, I kind of did. I don't want to do all of them. List the intersection of P and Q. So intersection of P and Q, what do they have in common? 24 for sure. And I think 48. That's where those two things will intersect. Like, where the multiples of 6 are also the multiples of 4. There's 24 and 48. P union Q. So I would put them all together. I don't want to do that. But it would be 4, 6, 8, 12, blah, blah, blah. Then show that if you add the union of P and Q, it equals the number of P, the number of Q minus the intersection of P and Q. I would have to actually do all that, which I didn't do. So I know this is 2, and I didn't figure out these two because I was too lazy. Well, I'm going to end there. But it would have worked. I guarantee you, because that's a formula that we have. Anyway, that's it for this lesson.